Thank you all for having me. It is my pleasure. I think this was such a perfect intro, so I'm just going to dive right into it. So what I personally think is the most exciting thing about being a roboticist today is that robots kind of are doing stuff. Like, when I started my PhD almost 10 years ago, I never expected that today I could go take a fully self-driving car ride in downtown San Francisco. Or when I started my PhD and my advisor told me, get the robot to pick up a cup and put it somewhere else, it was so painful. But now, as you can see from some of these demos from TRI, with just a few demonstrations and a little bit of time, our robots can actually finally pick and place stuff. At the same time, it's precisely this wide-scale deployment and increased capability that has gotten people all over the world concerned about safety and reliability. This includes industrial stakeholders. For example, DeepMind has an entire team on AI safety, and regulators, like the prior administration had an entire executive order on AI safety. But the thing that comes to my mind is that when we deploy robots truly at scale, truly in the open world, what safety means is actually a really, really nuanced concept. I like to start with an example that might seem simple. Why does it seem simple? Because I think we can all agree that a straightforward specification of safety for something like driving is don't collide. And if we look at this example from Tesla driving on the Bay Bridge here in San Francisco, for some reason this Tesla self-driving car does a hard brake in the middle of this road, causing a multi-car pileup. Now, why do I like this example? I like this example because oftentimes when I tell people that the safety spec is collision avoidance, they tell me, well, just tell the robot to stop. Okay, but here it was precisely stopping that caused the safety violation. Okay, and that's because the first challenge we face in safety is even if the safety specification seems simple, decision making is very hard. Super, super context dependent. However, I think safety is much more than just these kinds of interactions. Consider the right-hand side, this fantastic work from Professor Ani Majumdar's group at Princeton in collaboration with DeepMind. Here, a robot is using a large language model as a task planner. This task planner generates some options for the robot, and in this paper they argue, rightfully so, that a safe robot should be one that asks for help when it's uncertain. There are multiple options that are likely here. What I also like about this example is it reveals another kind of safety concern. Why are you even suggesting putting a metal bowl in the microwave? And last but not least, consider this Roomba. It literally breaks free into the open world. For some reason, I don't know why, this Roomba does not understand the consequences of going a little too close to this edge and dipping it. Okay? So the fundamental question I'm really, really interested in is what does it mean, or how can we go about generalizing robot safety? And a lot of my technical training, the way I think about these problems is sort of grounded in my prior work, thinking about robust control theory. Now, this type of safety has steadily been making progress over the past several decades. This is a very non-exhaustive list of increasingly more complex robots that are using these kinds of frameworks for safe control. Now, here, safety typically means constraint satisfaction. What I really like about this mathematical framework in theory is that it really beautifully captures something called feedback loops, essentially how the robot's actions are going to influence long-term outcomes. In addition, I particularly like how in this framework, the detection of an unsafe event is coupled with a mitigation strategy, what the robot should actually do to resolve a safety concern. However, for the longest time, this very general mathematical framework has been limited to hand-designed state representations, hand-designed dynamics, and failure states. Any student who has worked with these tools knows the pain of writing down that state space, writing down, for example, a collision checker. It's hard. It's a lot of hard work that only experts can do. At the same time, simultaneously, this other domain has been also making a lot of progress. Very broadly machine learning, but in this case, I'm gonna focus in on generative AI. My first introduction to these tools was through trajectory forecasting. Why? In trajectory forecasting, we do not know how to write down the state of what is going on in your brain. I do not know what is going on in your head, so what I can do is I can use a lot of data to maybe infer this just from the high-dimensional observations. In other words, what these models really excel at is learning latent representations of the world that I can't write down in first principles necessarily. They also are really easily guided by non-expert feedback. I'm sure all of you have given a thumbs up, thumbs down to ChatGPT and gotten it to do a better thing. You did not have to understand how GPT works, and it still did a thing that you wanted a little bit better. The problem, though, with these kinds of paradigms is oftentimes when we think about safety, we often focus on something like anomaly detection or uncertainty quantification, which are very important for thinking about the component. But they don't tell the robot what to do. So here's a really beautiful paper from yours, Marco Pavone's group. And this example I really love. So it turns out these large language models possess the capability to detect that this is a really weird scene. It's a really weird scenario to see the Cybertruck with this light post on the back. But the question remains, even though I know it's weird, what should the robot do? And so my hypothesis that my group has been exploring is, how can we systematically unite the best of both of these worlds? How can we systematically take the things we know and love from safe control and take these ideas or principles we see starting to work in generative modeling and start to generalize robot safety to the truly open world? Now, over the past 2 years, my group has done a bunch of work along these lines. We've done things just focused on these generative models used in robotics. We've done things like alignment and uncertainty quantification. We've also looked at their intersection as well. But today, my focus is going to be the following. I want to start by laying down some foundations. Let's all get on the same page with what I mean about safety more concretely. And then I'm going to talk about 2 very, very new works that just came out because I know everyone only wants the hottest stuff off the press. All right, let's just get into it here. So let's start by learning a little bit more about what I mean by safety. And to understand this, let's take a look at a running example. This is from some of my older work, in fact, in collaboration with Professor Somil Bansal here. And this was some work during my PhD where this robot is navigating through this environment, and it's using a policy that is really good at exploring. It can kind of figure out where to go to make its way towards some goal. However, this base policy, I'm going to call it, is sometimes overly optimistic and decides to cut corners in ways that lead to unsafe outcomes. So I want to use this powerful base policy. It is generally capable, but I want to minimally modify it to stay safe. And the idea from control systems we're going to use here is something called a safety filter, which is essentially a mechanism by which we can monitor any policy's output so that present actions do not result in a future failure. The big trick is, how do you get it? So to construct a safety filter, you need 4 ingredients. Okay, first, you need a state space. In this low-dimensional example, it's easy. Positions, velocity, orientation. You need a dynamical systems model. This can be a discrete time or a continuous time model. It could be a high-fidelity simulator. The key is that based on what the robot does, the state evolves. And oftentimes in robust control, you'll have an additional input here, D, which sometimes is called an opponent or a disturbance, which lets us inject more robustness into the overall system. For example, robustness to another agent, or external forces, or hard-to-model aspects of the environment. Okay, last but certainly not least, we need to represent failure. And here, in this example, if I know my environment perfectly, my failure set is easy. It's going to be the subset of the state space, subset where the obstacles are. Okay, so let's actually cook up a safety filter together. I'm showing you the safety spec here one more time, the subset of the state space where the obstacles are. And the particular synthesis technique we're going to be using for computing a safety filter is something called Hamilton-Jacobi reachability. Okay, the way we're going to do this is we're going to encode the failure set in this functional form by the sign distance function. Negative means you're inside of the obstacle, positive means you're outside. And we now want to know for any initial state of the system, like I'm here, does there exist an action the robot can take so it steers clear of the failure set? And this has to be, in theory, true even despite this worst-case disturbance that I told you about earlier. Now, formally, this is a safety-critical game whose value is defined up here. For those of you who haven't seen this, don't worry too much. The most important takeaway here is intuitively, this value function remembers the closest our robot ever gets to failure under the best strategy that it can possibly take. Now, thanks to decades of progress, we can start to solve this safety game with a myriad of techniques. In a low-dimensional setting, you can use high-fidelity PDE solvers over a grid, perhaps. For high-dimensional systems, you can maybe use something like adversarial reinforcement learning or self-supervised learning. And here is this value function being computed in front of us, just so we can see how one solver might act in the wild here. So one more time, that value function is being computed backward in time, essentially like a Bellman style update. Okay, let's take a look at what we actually end up getting. What is this safety filter? We can extract two quantities which define our safety filter. First is a safety policy. It tells us what to do. And second is a safety monitor or safe set, which tells us when do we have to start doing something to preserve safety? What is the last moment I could ever take a safe action and prevent future failure? And that's precisely the interior of this red boundary I'm showing you here. Here, for different initial states of our little robot vehicle, I'm showing you what the optimal safety control might look like. You're steering, really hard away from the obstacles. It's very intuitive in this low-dimensional example here. To actually do filtering, a really simple scheme you might employ looks something like this. Pick your favorite policy as long as your monitor returns greater than or equal to 0, or greater than 0 here. It says you're safe no matter what you do. If you get close to the boundary, which is the last moment at which you have an opportunity to make a safe decision before you're doomed, you have to switch to the safety policy. There are much smarter, fancier ways of doing safety filtering. I'd highly encourage you to look at these 2 review papers if you want to look for more details, but this is the simplest scheme you could possibly instantiate. All right, if we put this kind of methodology back in our running example, you'll see that safety filter right here on the upper right-hand side. That red boundary, in this case, is actually growing and changing as a function of the data we're observing. In this case, the data being a new occupancy map of where the obstacles are. And you can see the safety policy is preventing our kind of exploration-driven policy from taking these overly optimistic actions that might lead it to collide. Okay. This is the setup. This is the framework in which I like to think about safety. However, if you really, really look at a lot of safety papers that use these kinds of tools, you're going to see that under the hood, the majority of safety representations are collision avoidance. So here I'm picking on a lot of my own work. I'm also showing you a very non-exhaustive list of other folks in the community. And when you really stare at it, it's going to be things like distance to other agents, distance to obstacles, distance between my head and the ground. It's collision. This is a very important representation of safety, no doubt, but these are the kinds of safety concerns I'm really interested in right now. Okay, I'm really interested in things like tearing, breaking, spilling. Okay, so what's holding us back? Why can't we solve safety problems for these kinds of representations? Well, for this, we have to go back to our 4 ingredients for safety and start doing a little introspection. So I hope all of you are awake. We're going to do a little quiz now. All right, so here is an example. This is a robot manipulator in my lab. There's a bag of Skittles and it is opened. If my robot happens to do something like this, grab it from the bottom and pull up, we see this spill failure happen. Time for the quiz. If you had to model a state space, what would you put in your state space? Feel free to call it out. Whether the bag is open, okay, nice. Anything else?
We checked if the bag is open.
Yep. Other things.
Where's the bag? Where's the gripper?
Mm-hmm. Yep. Pose of the bag, pose of the gripper, yep. What about the Skittles?
Can we use insider information?
Can we use insider information? What does that mean? Okay, don't spoil it. Don't spoil it for me. No, but we're hand designing our state, right? We're trying to think about that first principles way I was telling you about. One time, so when I gave this talk in the RI, one of the senior faculty was like, oh, wait, what about the color of the Skittles? Do we have to include the color in the state? Maybe. If my constraint is never drop those red Skittles because they're my favorite, you better have color in your state space. What about dynamics? How would you model the dynamics? We just talked about all these different components of the state I could put in here. The bag orientation. By the way, no one said actually the deformable bag structure. Sometimes people say like, oh, I want to have a mesh to represent the bag itself because it's deformable. Okay, so the weight, yeah, that could be something I need as well. But what about the dynamics? Yeah, so you need to somehow model the way in which Skittles spill. Yeah. Maybe you might try to use some kind of fluid dynamics model maybe here. You could totally try this out. It's really hard to do though. And last but not least, what's our failure set? What's our failure set?
Spill.
Yeah. How would you mathematically encode a spill here? What would you measure?
Well, the ones on the table are okay. If it's the floor, it's bad.
Well, in this case, good. I like that. I like that. This is a totally legit safety spec that is personalized to you. Some people would not eat it off the table. Our tables in our lab are kind of dirty, so maybe kind of similar to the ground in that case. But in this case, the safety spec is don't spill out of the bag. But for this, right, when the Skittles are inside the bag, you don't even know where they are in the bag, so how can you measure the distance between the Skittle and the table? That's tough. Okay, so I would love to solve this problem, but the question is, how do I go beyond collision avoidance? As soon as I start thinking about these problems, it just starts to feel intractable. And what we all just discovered together is essentially we need to somehow go beyond these hand-designed state and dynamics representations because they are simply really, really hard to scale. And this is where we're going to take our first really big leap. Okay, we're going to go from all of these foundations all the way over here. And we're going to talk about how to generalize our safety principles, okay? So here, it might seem like all hope is lost. It might seem like, man, we don't know how to write down state or failure. But there is one thing going for us, which is that failure is observable from high-dimensional observations. If I show you this image, you say, yep, there's definitely those Skittles on the table. The problem, though, is that to do control, to do planning, I need to predict if the robot's actions are going to lead to this spill. Once I'm seeing the spill, it's too late. It's too late. And so this is where we had an idea where we said, okay, what if we start taking all those control theoretic tools, we start doing safe control directly in the latent space learned by these very modern generative world models. And I'm going to go into these details in a second here. Okay, at a very high level, it's going to mathematically look not too difficult. But that's how it always looks when you look at math. Before we had this state space X, we had our dynamics model, and our failure set was a subset. Now we just made everything Z, latent space Z. Now, if we dig a little bit deeper here, this is what we had before. These were states. We have this complex collision checker. We had our simulator or our first principles model. Now, the equivalent of each of these models looks something like this. Our state space is going to be an embedding of, in theory, a history of observations, for example, like images. Our failure specification is now simply a classifier on the embedding state. It's telling us, does this look like a failure? And then our world model is going to be our dynamics. And let's first talk about what this really is. So if I want to build a world model, this is essentially like a system ID problem. It's a very, very hard problem, but here's how they kind of work in this modern paradigm. I give you a data set of observation and action pairs. The observations throughout this part of the talk are going to be proprioception data for the robot, plus the wrist camera and the third-person camera that watches the scene. And then we have the actions here, which are going to be delta and effector poses. Given this data set, I'm going to train the following model. I'm going to first train an encoder, which is going to map observations to some posterior latent state, ZT. And then given this, I'm now going to train a dynamics model, which is going to predict how our current latent state and this corresponding action transition to the next latent state, Z hat, T plus 1. And since we know the true next observation in our data set, what we can do is we can train our model with a variety of self-supervised losses, such as reconstruction or teacher forcing, when we're trying to make sure the model is predicting or is imagining the next latent state correctly. I am not innovating on these models, by the way, here. We are building on really fantastic work from the model-based RL community and from the generative modeling community. Specifically, the two works we build on are at the top there, that's an older paper called Dreamer. At the bottom, this is a very new paper from Laurel Pinto and Yamakun's group called Dino World Model. And these are really nice modeling paradigms for getting this kind of structured model. But there's much to be innovated on this as well, if you're curious. Okay, we have two ingredients, state dynamics. What about our safety spec? Okay, well, recall how I said that failures are observable. This means that I can just look at my data set and I could do something like label, okay, is the robot already in failure or not in these observations? Okay, so on the left-hand side, we're good. On the right-hand side, the Skittles are already visible, so that means I'm already doomed. We can encode each of these observations into our latent state, and now our safety spec problem becomes a classification problem on this latent state. I'm not going to show you the details of the actual loss function. You can take a look at the paper, but intuitively, here's what it does. Essentially, you're penalizing latent states corresponding to observations in the failure set from being labeled positive, and vice versa. Why? Because if we go back to our reachability formulation, we remember that the way we were encoding failure was via that sub-zero level set of this sign distance function L here. Okay, so we need any latent state that returns negative is going to be in our failure. Okay, great. We have state, we have dynamics. We know our failure. Let's compute a safety filter in latent state space. This is formally the optimization problem we have to solve here. Now, by the way, for those of you who are more familiar with, for example, model-based reinforcement learning, you'll notice that the key difference here is this min over time rather than expected value you might see, or sum over time. And that's because we need to remember the worst that ever happens, the closest we ever get to failure. All right, so here is a visualization of the latent state space. By the way, it is not going to be this pretty in reality. This is just a graphic. And what we're essentially doing is this inner L of x, or L of z, sorry, it's going to define some subset of the latent states, where if I chose a latent state here, and I decoded it, it would show me something like this. It would show me Skittles are on the table. Now, given any initial observation, we encode it into our latent space, shown here as a dot, z0. And our safety analysis is now reasoning about the robot's best efforts to avoid this unsafe region, these failure regions in its imagination. But remember, we're not doing any real rollouts in the environment. We have built a model, and now we're doing control in the model. If at any point, the robot has tried a bunch of trajectories and it has discovered all trajectories lead to failure, that value function is going to remember a negative number. It's going to say all roads lead to failure, you are doomed. And that's where that min over time comes into play. So in other words, given the best effort to avoid failure, how close does the robot come to failing? Now, to solve this problem more tractably than just forward simulation, we can derive a latent safety Bellman equation shown here. And if we were to solve for this value function backwards in time, we would see this latent unsafe set growing over time, encoded as the latent state where the value is less than 0. And here's an example of one such state. This situation, where the robot has already picked up the Skittles bag so high up, no matter what the robot does, if it reorients or tilts or anything, it doesn't matter, those Skittles are coming out. And that's the gap between the failure set, I see the Skittles on the table, and the unsafe set, which is, in the near future, there's nothing I can do, but those Skittles are going to come out. Now, the last one important thing I want to mention is this computation is, still subject to the latent state dimensionality. And that's still very large. So for example, in some of our experiments, the latent state space Z is like 512 dimensional. This is still much better than the raw observation space, to be clear. Given 2 wrist cameras, 3 channels, and 128 by 128 pixel observation space, that would be 98,000 dimensional. So it's still better. We're leveraging the compression from the high-dimensional observations, but it's still too high to solve this problem exactly in a grid-based fashion. And so we approximate the safety value function via essentially doing reinforcement learning in the world model. And this is just a modified Bellman backup that is compatible with a lot of off-the-shelf RL techniques because it induces a nice contraction mapping. This is not our invention. You can take a look at this paper for the details on the original connection between reinforcement learning and reachability analysis. All right, ultimately, after we do this analysis offline, we get our safety monitor and our safety policy co-optimized that's ready to be deployed. As a reminder, here's the environment context. Here is the observation the robot sees. It's going to get mapped to some latent state Z. And as the robot executes some nominal policy, we see here the latent state moving through the world model. At some time ZT, though, our safety monitor detects that if the robot continued along that nominal policy, it would be doomed to fail. And this is where we take over. We do that filtering technique, and we say, nope, you have to now apply that safety strategy instead. Okay, we have to do a sanity check, though. We've done a lot of approximations. How close does latent safety get to a privileged safety? So here what we do is we do a computation on a benchmark safe control task. This is all of our favorite tasks in safe control. It's a Dubin's car 3D model. It only controls the angular velocity. And there's this circle in the middle of the state space, which is the failure set. Our latent model sees these observations, images plus the heading of the robot. By the way, you might ask why heading. So the image resolution we pass into our world model is like 128 by 128. So actually the robot becomes a point in the pixel space. So it's really hard to tell what the orientation is. If you had a higher fidelity representation of the image, maybe you wouldn't need that theta. All right, the data set is 2,000 random trajectories of the robot moving around. Our world model is just an off-the-shelf dreamer model. That's a recurrent state space model. And our failure classifier is trained on the same labeled data as our world model. Okay, here I'm showing you, on the left-hand side, the ground truth failure set inside of that dashed line. And in the center on the right-hand side, I'm showing you the ground truth unsafe set for two headings of the Dubin's car. Theta equals 0 is pointing like this. Theta equals pi over 2 is pointing like this. And this is ground truth in the sense that we compute it via a super, super high fidelity grid-based solver. If I give a reinforcement learning based solver the privileged state and access to the ground truth dynamics, this is how close we get to approximating the unsafe set. Okay, so you can think of this as any error is coming exclusively from RL approximation, but not from the representation of the problem. And you can see the F1 score on the right-hand side, so quite good. This is across all X, Y, theta states. Here's latent safety. Okay, so you'll see that the learned failure classifier, a little bit more conservative. We incentivized it to be a little bit more conservative during training. But the unsafe sets, the backwards reachable sets, also quite high quality, despite several of these approximations. So you can see the F1 score on the right-hand side. Okay, and I want to really stress that the latent safety only sees these observations. But in this simple example, we know which of these observations correspond to which privileged states, which is why we can do this controlled analysis. All right, this is great, but let's scale up to visual manipulation. So here the robot has to pick up this green block, and it should never topple the red ones. It's a very hard task. They're really, really, really close to each other. Even I, if I teleop this, would really struggle to do this. Now, the nice thing about this problem is that as a stakeholder, I can easily identify what the failure set is. And by the way, the failure set is not a collision avoidance spec. The robot can touch, push, tilt those red blocks as long as they do not fall over. Okay. So let's see how our safety filter, how our models perform when we give them a known unsafe observation sequence and action sequence. So here is that video I just showed you, but like timestamped like this. And I'm going to show you what both the failure classifier and the value function say over this trajectory. At the beginning of the trajectory, life is good. Both of our methods say, well, at the start of the trajectory, you're not failing and you're not doomed. Same deal at the next snapshot. Now things get interesting though, because at t equals 14, the robot has approached the center block so quickly, and it has ended up touching those red blocks with high enough force, where soon those blocks are doomed to fall. And so this is why we see this latent state already being in the sub-zero level set, or the backwards reachable set that we computed. It continues to say you are still doomed, you are still doomed. And at the last time step, our failure classifier says, yep, now I definitely see those blocks falling down. You are in failure for sure. Let's see our latent safety filter protecting this base policy from toppling over some red blocks. The difference, by the way, between the left and right images is on the right-hand side. It's just a slightly different initial condition of those blocks. They're moved a little bit in front of the robot. So it's two different initial conditions. The data you see here is exactly the same data that the robot gets to see. Every time you see the border lighting up in green, it means the safety controller is active rather than the base policy. And as the base policy approaches the blocks too fast, the safety filter activates and is slowing the robot down. Only after the robot backs up a bit does the safety filter actually let go and let the robot finish the task. And you see that those red blocks are able to be perturbed. They can move around, but they don't fall down. I'm going to summarize some of our quantitative results here. So what we did was we said, okay, how much better is our latent safety filter compared to other latent control strategies you could apply? So all of these methods use the same exact world model, same exact data, nothing is different. The only difference is the objective. So the top, baseline dreamer, has soft constraints. You're kind of co-optimizing, grabbing the block and not toppling over the red blocks. The middle one is a constrained MDP formulation. You can think of this kind of like an empirical risk of violating a constraint. And then ours is this safety policy, which shields. And you'll see that across the successes, violations, and incompletion rates, ours is not perfect. We still fail 20% of the time. It's a really, really hard task to do. But what you'll see is that this balance between success and failure is a little bit better than if you were, for example, tuning a risk threshold, which is really sensitive. Tiny change in the risk threshold, huge performance difference, those middle two rows. And tuning rewards, I'm sure as all of you know, it's quite difficult to actually really, really find that sweet spot. And that's what the first line is showing. Okay, but the ultimate test is going to be in hardware. Let's see if this actually works. In hardware, we're going to return to our Skittles example. This is the data the robot gets to see. Third-person camera, it's like right here, looking like this. And the wrist camera. Let's watch one more time. So my student here is going to be teleoperating this robot. And here we see that failure we saw from before, where if my student happens to choose this wrong grasp, all the Skittles come flying out. For world model training, we use 1,300 trajectories collected on the robot. Of these, 80% are random. So my student just samples from a Gaussian and just lets the robot bumble around. 10% of them are explicit safe demonstrations, where my student was showing how to pick up a bag from the top. And then 10% of them are explicitly unsafe, where a spill is induced by my student. Why do we have to have this data? Well, the model can't predict what it hasn't seen. Okay, given our trained failure classifier on this data, we compute offline this backwards reachable set in the world model via that process we saw before. And then we can deploy. Okay, on the left-hand side, you're going to see that when my student chooses to grasp from the top of the open bag, life is really good. You see that boundary, green boundary, is never showing up. That means he's fully in control the entire time. But in the middle, what he's going to do now is he's going to grab the bottom of the bag and start to shake side to side. As he shakes, you see that occasionally that green light is flagging, and it's because the filter is slowing him down, because it knows that if he shakes too hard, the Skittles will come out. Last but not least, if he grabs the bottom and pulls up really sharply, it completely overrides his commands. I also want to show you a continuous, like an uncut version of this. If you're ever in Pittsburgh, please come to my lab. You can mess around with this. It's a lot of fun. So once again, I'm showing you that robot POV on the top, and then on the bottom, I'm showing you the value of the next state, assuming I executed the teleoperator's actions. So the value is really good at the beginning. It's positive. Teleoperator's doing a good job. When he starts to shake, you start getting close to that boundary. You're getting to a danger zone, and that's why the safety filter has to kick in. Then when he grabs the bottom and pulls up, you're going to see that value drop really, really, really sharply. Because if we continue to pull up, we would definitely be doomed. The next thing I did was I bought all the Skittles I could find in the Pittsburgh neighborhood. And I gave them to my student to say, okay, does it work with other Skittles? So remember, we only trained on the red Skittles. We deployed here with sour, wild berry, and smoothie Skittles. It generalizes. We tried to change the background. It also works. This is an in-distribution orientation, but it also works out. I'm not going to cover another example here that you can take a look at our paper. We can take the same exact filter because it is policy agnostic. And instead of shielding a teleoperator, you can shield any other policy. So we shielded, for example, a diffusion policy that was pre-trained. And we also find that it decreases the percentage of the Skittles that are spilled. But what I want to quickly show you guys is some dirty laundry. So this is not perfect. Again, it is learning-based. We we are just beginning to understand the limits of these components and how they work together. This existence proof is exciting, though. Some of the failures we've seen that are quite interesting are the following. This is an observability issue on the left-hand side. If you rotate the Skittles bag 180 degrees, and so the opening is not observable by either the wrist camera or the third-person camera, the filter is like, yeah, it's a closed bag. You're good to go. And that's why it doesn't override. Okay, on the right-hand side, I bought my students some peanut M&Ms. Peanut M&Ms are much heavier than Skittles. In fact, I didn't appreciate all the different bag types, by the way, before this project. Peanut M&Ms come in a papery bag. Skittles come in a plasticky bag. Very different dynamics. Since we only trained on Skittles, if we put the M&Ms bag down, the filter is not reliable. It's overly optimistic and fails to protect the robot. Maybe this would go away with more data. I don't know. But for this particular setting, we didn't find this generalization across dynamics, which is not too surprising.
Well, sorry,
yes, please.
Can I ask a question? I mean, but the information that it's using is just visual information. Where one end of the bag has sort of a look up and open end of the bag, and another end doesn't. Why should whether the M&Ms are heavier or the bag is more papery really make any difference?
Because the value function depends on the dynamics prediction. And you can't accurately predict the dynamics of this bag that's aggressively out of distribution. So the model... So I thought the same thing, and then my student told me to interact with this bag with the teleoperation setup. It is really, really hard. Again, that paper versus plastic and the heaviness of those M&M Skittles, in our tiny data regime with just the Skittles, it just doesn't generalize, unfortunately.
And how does it... Mm-hmm. And the way you're not sensing, are you sensing forces?
No, maybe implicitly it's weak to some of the perception, but exactly, yeah. Yeah. So again, it's hard here, by the way, to disentangle. Is it an observability problem? Like maybe we need more sensors. Is it a dynamics modeling? Like it's really hard to disentangle this. We recently were trying to diagnose if it could also be the visual differences, like the text M&M looks different than Skittles. So we looked at so for example, the model we used here uses Dino encodings. We looked at the top 3 PCA dimensions of the Dino embeddings to see if they're similar. They look pretty similar. Maybe it's some higher order PCA components that matter a lot. I don't know yet. It's really hard to diagnose this. And if anyone has thoughts or would like to work on this, please let me know because I'm very curious about understanding the limits. Yes?
Reachability and kind of uncertainty, as you said earlier. Can you do one thing where you can online estimate the uncertainty of the dynamics because you have to learn more and then you can see what's happening? And maybe that would help with some correction. It's not foolproof, but it might help with some.
Yes, we're working towards a Coral paper that shows. No, don't apologize. This is great. I had the same exact question as soon as we saw this. So, yeah, we're thinking of how to inject or model uncertainty. If you do it carefully, it can help a lot with the robustness. We're not 100% there yet. I think there's many smarter ways we can do it. We have just one attempt at the problem.
So the framing of the problem at the beginning, you have state space, and then you have dynamics, then you have the failure mode or the bad guy or whatever it is. I'm thinking about a very specific problem from the real world.
Yeah.
You have a mobile robot, you're trying to deploy it. We want it to be safe. Safe means don't fall down the stairs or insidiously an escalator, right? Because you don't see the escalator, you don't see the stairs until you're on it. The problem is mislocalization. So you have the state space I'm moving from one to the other. How do you represent that in this framework? Because if you start off mislocalized, the whole framework goes out the window.
Yeah, maybe the current thing we're exploring, which is maybe part of your question, is essentially if you think about what the encoder is kind of trying to do, it's kind of trying to do state estimation for you. And sometimes you need to gather more data or be a little bit more active about knowing whether or not you actually know where you are or what the environment is like. And so we've been thinking a little bit about what does it mean to do kind of active exploration in these world models. to get a better sense or a more confident sense of exactly where you are, so then you can do safe control.
Yeah, the danger is, of course, if you're actively exploring and you get onto the escalator and now it pulls you down, you're in the bad situation.
Agreed, agreed.
What we ended up sort of adding sensors that give you secondary guarantees against that.
Yeah, and that, by the way, I think that goes back to the discussion about observability. Like, if you have more sensors, then you can have a higher quality estimate of where you are, and therefore you have a better estimate of are you going to be doomed soon. And so I think we have other directions we're thinking about how to essentially use better other sensors to get a better, more accurate representation of if you're going to be failing or not. There was a question in the back as well. Yeah.
I was just wondering, during data collection, did you change the orientation of the bag?
Yes, that's why, if I go back here, so this is in distribution, a different orientation of the bag. But we never, like, the full 180 tilt, you just literally can't see the opening, so, like, you don't exactly know how to interact with it. Oh.
If you say you just train an imitation learning pipeline where you only show demonstration with the correct grasp,
Yeah.
how does it compare to that with experiments? Because I would think maybe that would also work.
There you go. So I didn't go into these details for the sake of time. You can take a look at the paper. Essentially, if you just train it on safe data, the policy is overly optimistic. Yeah. So your spill percentage is much higher. Again, in theory, if you collect enough data, you could eventually get there. But if you have trained imitation-based policies, I don't know if you have, you know that it's non-trivial to get them to actually be really reliable. Yes?
I had a question about data collection also, like with the 1,300 random orientations, was your PhD student like manually doing all of those, or was that like
No. So remember, 80% were random. The way that we got this data was from sampling from a Gaussian in the action space and then just executing it. So 1,000 trajectories were random.
But what does the like random sampling actually look like?
You just like randomly choose an action and then you execute it, and then you sample again and then you execute it. You can take a look at the paper as well for more details. That's part of the beauty of doing something like building a model, is that actually you don't need perfect data. If you think about how a lot of the times data curation is very important, it's still important in building models too, but even random data is really helpful because it gives you a model of outcomes, which is really, really useful for planning. While, for example, for something like imitation, you'd only use that 10% of safe demos. You would never want to like have your policy memorize random actions. In the back, yeah.
Where the model was focusing throughout the duration of its action? Like, was it looking for like, oh, is this like a white edge? Or like, how was it actually going through that?
So in general, model interpretability is very hard. That's what I mentioned earlier, where like you can look at the, let's say, top 3 PCA dimensions of the encoded images as a proxy. So for example, if you look at this in our case, you'll see things like the model has learned to segment out, essentially, the bag from the background. It knows that the gripper is different from the bag. So it has some notion of like instance segmentation. But I don't claim to actually fully be able to interpret the model's understanding. Yes?
What are the pros and cons of this method versus using like imitation learning from an expert demonstration?
Yeah, so as I just mentioned, I think that there's nothing wrong with using imitation. In fact, that's a great way to get a base policy to do something generally capable, like I mentioned at the very beginning of my talk. I think there's 2 things that are really helpful. One is from a data perspective. When you train an imitation policy, you're actually throwing out a lot of data usually. What you'll do is you'll like collect some data for the policy, expert data, and you train the policy, you do some rollouts. Those rollouts, by the way, you never end up looking at again. You just look at them for eval. Then you see that your policy kind of sucks, so you collect more data. Then you put it back into your policy, and you keep doing this. And you end up using a tiny fraction of your data set for the actual policy. What if you used all that data, you just shoved it into a world model, because that model doesn't care about the quality, it just wants diversity, to learn how to predict outcomes of what's going to happen next. So I think it's a really nice complementary way of using all that data you're generating to building a better understanding of the world. And the second thing that this is really helpful for is that, again, in my students' experience, it is very hard to actually get these imitation-based policies to do the right thing. And so this is an additional layer you can have on top of this, where you can try your hardest to get recovery behaviors and have the base imitation policy do the right thing, but you have this extra sanity check at the output that just makes sure that these hard to model, hard to encode constraints are actually enforced. Yes?
So 2 questions. First one, for the dirty laundry slide.
Yeah.
Is there a way for the robot to look, or for the sensor to look at the bag, or maybe touch the bag a little bit, and then realize that maybe you shouldn't pick it up? Because it's unsure. That's the first question. Second question, who ate the Skittles?
Oh, okay. So first question, yes. So this is related to some of the directions we're trying out in the lab now. Basically, some active perception. Like you need to model that. It is hard to do though, but there's things one should do.
Is there like a OD detection, like you use for hearing, and you just realize I haven't seen this before?
Oh, our Coral work will give you some answer. And then your second question, no one eats the Skittles. They're disgusting. They keep falling on the ground during our experiments, so no one eats those, but we're always finding more of them. Okay, hold on. For the sake of time, I want to make sure I get to the second half of my talk. I'm happy to chat more later as well. So sorry to keep going for that. All right, let's keep going though. And I want to quickly do another deep dive into some of our recent stuff. So remember, I said safety spec is a classification problem. Who gives you the labels? Okay, this is who gives me my labels. My hardworking student, looking at those videos, labeling. I would argue again, watching videos to see where the Skittles are, way easier than writing a collision checker, way easier than giving tons and tons of teleop demos, but it's still a lot of work. However, more fundamentally, the actual thing that this reveals is that if you really think about it, the failure spec that tells you what is safe or unsafe, it's very context dependent. For example, grabbing the chip bag really, really tight by the center, okay, that's safe if I'm making a crunchy topping. It's unsafe if I want to eat that snack later. So what I really need to do is I need to make sure that I can kind of adapt what I mean by safe or unsafe, what I mean by that failure classifier, depending on these contexts. And so here's where we asked ourselves, can we somehow use knowledge in these pre-trained models to be kind of a context-dependent failure detector? And this is where I'm going to touch on the last work here. We're calling it VLM in the loop policy steering. All right, here's the setup. Same robot, different task. This task now is to serve a cup of water to the guest. The base policy, since all of you are asking about imitation, the base policy is an imitation-based policy. It's a diffusion model trained on a bunch of diverse ways of handling this cup. Okay? What do you do at deployment time? You sample from the generative model. These are different samples that come out from this multimodal policy. The problem is that not all sampled actions result in the same task performance. For example, if I happen to choose this mode, this sample is really good. It grabs the cup by the handle. But there's another situation I can get into. I sample this mode, and in this mode, the robot does the task, but it puts its fingers in my cup. That's not great. Okay, last but not least, you can also sample a mode that when you execute, it just totally fails. It's really hard to know this a priori. That's why you have to do tons and tons of rollouts in the real world to know if your imitation policy is really good. But the key thing to notice here is that this base policy actually does contain the right behavior. It is useful. But what you need to do is verify that the robot's sampled action plan is actually going to lead to the outcomes you want. Okay, mathematically, how can we think about this? You can think of this problem of what I'm calling here policy steering. There's a few other works that think about this problem as well. You can think of this as a model predictive control problem. Mathematically, here's what you're really doing under the hood. Your optimization variable is to select a sample. Here I'm just showing you 3 samples. But the problem is that because your base model is generating actions, and what you really need to evaluate them is you need to know outcomes. So you need to somehow translate the low-level actions into outcomes. For example, maybe in theory you would need to predict the future observation sequence, given the current observation and the actions. And then once you predict those outcomes, then you can evaluate them with some reward function that maybe is parametrized by some task context, like serve the cup of water to the guest, which in this case is written in natural language. This is a nice way of writing down the problem. It is important to know what you are solving, but how do you actually solve it is the trick. And so here we use the same key idea. We say, let's reason about outcomes in the world model. So here we're predicting those latent states again. And then let's align a VLM to directly reason about those latent states for evaluation that can easily be adapted depending on different contexts you give me. Here's how it works. We take those observations, we encode them into our world model. Here are 3 latent state trajectories that correspond to our 3 action plans that we sampled from the base model. If I decoded these trajectories, they would look something like this. You see these outcomes that correspond to what I just showed you, these different modes. Importantly, though, we are not passing the actual decoded images into the VLM. We have baselines like this. Please look at it. It does not work. What we do instead is we pass the latent states directly to the VLM, and we get it to reason about the latent states directly via essentially posing a latent text alignment problem for the VLM. So what we do is we take, in this case, Llama 3.211b Vision Instruct, and we fine-tune it via a video question answering problem. We're essentially given embeddings of the video that we have in our data set. We also have narrations, right, like descriptions of what is happening. And then we can ask the model to narrate what is happening in these latent states. By converting the low-level embodied state, Z, into a textual description, you are putting these outcomes in the native representation that the LLM is capable of reasoning about for really high-quality evaluation. And so what happens is we take those latent states, and here's the prompt we pass the latent aligned VLM. We say, the robot aims to grasp a cup from the table, provide a sentence that best describes these different latent states. It describes, okay, the robot's attempting to grasp the cup by the handle, sees the cup through the interior, or it fails to achieve a secure grasp. We call the same model, or you can call a different model, to now reason about these descriptions. And we say, okay, this is the task context. You're serving a cup of water to the guest. Please select the best action plan. And the model says, okay, the chosen mode is 1, because the most suitable way to serve the cup without spilling or contaminating the drinks is this one. So essentially, the VLM is also doing this argmax. All right, so here's the result. This is that same example I showed you before. These are some of the samples that you can possibly get. And if you use our VLM in the loop policy steering method, given this task context, the robot chooses to grab the cup by the handle. But if you change the context, you say the handle is covered in oil, it'll choose to grab it by the interior. Here's another example. Remember that chip bag example I showed you before? If you say avoid crushing the contents inside, it grabs it by the edge. If you say maximize stability, it's going to grab it by the middle. Same base policy. We are not touching it. We're not retraining it. We're just scoring the generations and choosing only the ones that are aligned. We also just deployed this for a longer horizon task, which requires reasoning about interactions between multiple objects. So here, the first situation our robot is in is it has to grab the fork. There's many ways to grab it by the tines or by the handle. And so the predicted latent states, when they're decoded into textual descriptions, reflect this. And the VLM says, okay, well, if you're trying to eat with this, I should probably choose the mode that touches the base of the fork and not the tines. So that's what ends up happening. And then we call our method one more time. We say, okay, what could happen next? And it says, okay, the robot can drop the fork outside the bowl. It can fail to place it in the bowl. Or maybe you can release the fork inside the bowl. That's good. That's the one I want. And then the model chooses that one. It's not fast enough to run like real time. We benchmarked it. It takes about 3.7 seconds to call this. You can maybe get it faster with distillation techniques, quantization, whatever you want. But this is more of like a high-level way of steering it. It's an interesting question to ask, like, when should you stop to think? That's a really cool question that a lot of LLM folks are thinking about. I think it'll have a non-trivial implication in embodied AI too. But this is what we've kind of seen. Now, one question you might ask is, what's the benefit of this two-stage pipeline? First, predicting with the world model, and then describing with the aligned VLM. And we actually tried this. So here we have this one baseline. This is the same exact llama model, fine-tuned on the same exact observation data. And this model takes as input the future action sequence, the current observation, and has to generate a textual description of what's going to happen in the future end to end. There's no intermediate latent state translation. And we find that this end-to-end model, given the same exact data set, really struggles to have high-quality task descriptions. It's too imprecise. If you take a look at why, so here's an example. This is from the cup and the bag task. These are the images, ground truth images that happen during execution. Here's what our method, which remember has to first predict the latent state and then describe it. These are the descriptions that our method has. Okay, it says something like, the robot seizes the cup through the interior or by the middle. If you ask the end-to-end VLM model with the same training data set, it struggles to capture really accurate motion details. It says things like, oh, it grabs the mug by the handle or by the corner. Again, maybe given more data it would work, but assuming the same exact training set, you can get a much higher quality understanding of the world by first having the world model, which is good at embodied reasoning, give you the predicted embodied outcomes, and then the LLM for just translation. Okay, so we've ended the deep dive. I have 1 minute for questions, which I'm excited to take. I'm just going to quickly wrap up here. There's much, much more to be done. These are just the first steps towards how we can kind of systematically unite the things that we know and love, underlie sequential decision making, i.e. control, with some of these modern models to scale us up into the open world. I want to say a really big thank you to my students and my funders, without whom this would not be possible. And with that, I'm really excited to take your questions. Thank you.
I think what we should do is take a few questions now, and then if there's more, of course, they can accost you during the...
Yes.
So,
questions. I saw some questions earlier, so we can return. Yes.
So when you implement the LLM, like kind of prompt the different steps for the robot to do, is the LLM also getting the inputs from the videos that the robot has?
So our approach only gets the latent state predictions. We have baselines in the paper that get the decoded images. Actually, I'll just show you really quick. So this is just a screenshot from the paper. So VLM image and VLM image oracle are both models that take as input images. Actually, they're both GPT-4o. So VLM image takes the decoded future image predictions and passes them into GPT-4. Sorry, that's VLM image oracle. Yeah, sorry, VLM image is the decodings. VLM image oracle is the ground truth future observations. And given the current models, GPT-4o, they're not strong enough to really narrate the fine-grained details of these embodied outcomes. But yeah.
Is on the safety filter.
Yeah.
Did you train the safety filter only with this one failure type of like spilling, or did you also include other failure types?
In this example, the hardware demo, it's only that one failure spec.
Okay.
Yeah. So you could imagine, and it's something we've thought about, like combining the adaptability of this VLM style approach with the latent safety filter approach to kind of adapt it. Yeah. I thought there was one more question earlier somewhere here. Yes.
I have a more philosophical question, I guess. So a lot of your work revolves around kind of generalizing safety to the open world, like the specification of the constraint, right?
Yeah.
But we're still using very classical techniques like reachability or definition of safety as like set-based safety. But I kind of had this idea when this gentleman brought up like the different definitions of safety. Like if you drop the skills on the table, this gentleman is like, okay, he's like okay with that, right? But to you, that wouldn't be okay. So it seems to me like there should be some sort of, I guess safety is kind of fuzzy in the real world, right? So maybe is there a way to generalize kind of safety beyond just set-based safety and maybe generalize these kind of set-based reachability tools to tackle that?
Yeah, maybe I'll answer your question in a few parts. So part number one is actually related to this person's question here, which is that if you think a set-based representation is correct, but you want to align it with a particular end user, like your two different definitions of that set, then what you really need to do is somehow like parameterize maybe your safety filter based on something that lets you easily adapt based on the context. So that's one way you can handle that. You're asking, though, another question, which is like, okay, what does safety even mean? Like, is it always a set-based representation? Is it something else? And by the way, for me personally, like safety is very like It doesn't have to be the set-based representation. I'll tell you when I think it's the right thing to use. For me, these hard constraint definitions are appropriate when the spec represents something irreversible. That's why collisions is oftentimes something that we represent in the set-based model, because once I hit someone, I can't undo that. If I break a glass, it's never going to be the same. It's true, Skittles I can put back in the bag. We just have to start somewhere. But I think that the most appropriate context in which you want this hard boundary are genuinely irreversible things. After that, there's a lot of different flavors of safety you can go for. For example, in the AI community, alignment is the main mechanism they talk about. And this is a much more like reward function-based way of thinking about it. It's a soft model. And it's more about like, are you doing what I want? And that's a totally legit other way of safety. You can also look at some of our early works that I showed you at the very beginning for how we can do alignment for some of these visual-motor policies. Yeah. Yeah.
Thanks for the totally amazing talk. Blew my mind. I loved it. Thank you, Andre. So my question has to do with how much data did you have to hand label with the latent codes with narrations in order to align the normal model? What's the volume of data we're talking about?
That's a good question. Okay, I am not going to give you the accurate number because I can't recall it exactly. If you take a look at the paper, I think it was a few hundred trajectories. Okay. Yeah, I think it was on the order of like 700, 800. But please check the paper for the details.
Follow up on that, how much kind of iteration, trial and error did it take to figure out what was important to narrate in the human narrations?
Oh, that's a good question. That's a good question. Honestly, my PhD student is probably much more qualified to answer that than me because she's the expert there. I think my intuition is something like this. So she was the one who did the narrations. We didn't use, for example, like a video narration tool that you could imagine scaling this up to do. If you're using a video narration tool, though, you need to now ask this question, how do you get the automated tool to narrate at the right granularity? For her, she kind of knew that, like, what the level of granularity should be because she's like a task designer. And so she knew that, for example, grasp poses matter a lot. But I think that your question is revealing a really interesting thing if you really want to scale this up. And I actually don't know how I would do it off the top of my head, but maybe we should work together and figure it out. I love that question. That's a good one. Yeah, in the back.
Can you tell me about what might be the current world models like do you have a model? What might be something that can be improved on?
There are so many things. Okay. I'll tell you top two things we've been thinking about and trying to fix. One is hallucinations. So specifically, here's the problem we have. So remember the Dubinskar example? We had such good coverage of all observation action pairs. That's why we got that really high fidelity backwards reachable set. In the high dimensional case, like with Skittles, we never have perfect coverage of all observation action pairs. This means that what happens is when you ask for simulation of an action that is out of view distribution, you can imagine things that are totally implausible physically. And so I think that's one place where uncertainty quantification plays a really, really, really key role. You need to know when you are imagining things that are out of distribution and don't make sense. That's something we've been thinking about recently. And then another problem that we've also seen is that the way that these models are trained, for example, if you do something like image reconstruction, a lot of the times you're focusing on parts of the visual environment that might not be relevant for the task. You're worried a lot about backgrounds, or maybe hyperfixating on certain distractors. And what happens is that at deployment time, if you add a new object or you somehow change the scene, you're not guaranteed that it's actually going to generalize. And so there are some other ways we have been thinking about how to use very general paradigms for just training the base model to be good in general. And then at runtime, making sure that it's only paying attention to the things that matter. Those are the top two things that come to my mind. Yeah. Okay. Sounds good.
All right, thanks so much.
Thank you.